So by the way, do you mind that we record your talk and make it um post your talk on YouTube?
Um, I'm okay with that, no problem.
Good, yeah, because we have a channel that we post the recorded talks in this series on YouTube to check more audience.
Yeah, sure.
Thank you.
Maybe I can share my screen.
Yes.
Okay. Yeah.
Yeah, so maybe I will first give a short intro for the speaker. So it's my pleasure to introduce our speaker today, Professor Tianbao Yang. And so he's a professor and Robert Richardson Faculty Fellow in the Department of Computer Science and Engineering at Texas A&M. So he is leading the lab for optimization for machine learning and AI. And his research spans optimization, machine learning, and AI with impactful applications in computer vision, natural language processing, trustworthy AI, and medicine. So Professor Yang has a very impressive track record, including the Best Student Paper Award at the COLLT conference, a computing theory conference. And in NSF Career Award, among others. So he is also the founder of the widely used Leap AUC library. And I also used this library before in my research. And he serves as an associate editor of top journals, such as IEEE Transactions on Pattern Recognition, Pattern Analysis, and Machine Learning, Machine Intelligence, PAMI. And please join me in welcoming Professor Yang. Yeah, thank you.
Great. Thanks for the introduction. And also I want to thank for the invitation. Hello, everybody. My name is Tianbao Yang. Today I'm going to talk about recent work. So the title is Model Steering for Improving the Scaling Laws. This is actually based on our recent ISML paper. So we're going to present that in next month. So this is the core contributions from my student Xi Yuan Wei. He has done great work. All right, so this is a overview. So first I will give you a introduction to the backgrounds and the motivation. And then we'll introduce a framework called DRO risk minimization. And then a method applying this framework to clip training called the DRO clip. And then finally, you have some time, I will briefly talk about the optimization algorithms that is actually from our earlier works, not in this SML paper, not a focus of this SML paper, but we use the optimization algorithm that we designed earlier. So I want to first want to highlight the my research interest, which is the intersection between optimization, machine learning, and AI. So if you think about machine learning is the core of AI, and then in my point of view, optimization is the core of machine learning. Because essentially, you need to solve an optimization problem for learning a good model. So that is actually my research focused on the core of machine learning, optimization, and for solving many important problems in machine learning and AI. So what is optimization? When you think of optimization, most people may just think about, okay, optimization is about algorithms, right? So there are many algorithms you can think about, like SGD, ADAM, ADAM-W, momentum, etc., right? However, in the research, when we talk about the research of optimization, it's not just about algorithms. Actually, it includes several other things. For example, the objective function. So how do we formulate a good objective function, right? That facilitate the learning, that give us a good model. And another thing, of course, very important thing is that how do we understand what is the generalization performance of the learned model? Right? So we leverage optimization algorithm to optimize certain objectives to get a model, but we want to understand how good is the model, right? Generalization analysis, generalization error. So optimization plays very important roles in all of the three aspects. And also we'll cover all of them in this talk, okay? So in the title, I also have the scaling law. So what is the scaling law? So that is actually a recent trend, especially in the large language models, right? So scaling law refers to empirical patterns showing that how the performance of the machine learning model improves predictably as we increase the training resources. That includes the model size, training data size, and compute budget. So usually if you plot the testing performance, generalization performance versus these different variables, it will have this power law kind of curve, okay? So if you can improve this scaling law, which means you can use less compute or smaller data size or smaller models to get a better performance, okay? So that could have dramatic impact in industry companies in the real world. And that is what we want to do. We want to improve the scaling law. Okay.
So can I ask one question?
Yes, please.
So is this about fine-tuning of a light small language model for a specific domain?
Actually, you will see that our framework is very general. You can apply it to fine-tuning, pre-training, but as an example, we will show you how to do the pre-training for the clip model. Okay. All right. So you may think about the data is a property, right? So companies train the models, but they never release the data because data is a property, right? But the companies also, but many companies, right, also but release the models, right? So I mean DeepSeek, Meta, Llama, and actually on Hugging Face, there's more than 1.7 billion models. Okay, there's a universe, right? Model universe in the Hugging Face. So I want to give this argument that a model is also property. Although that definitely for this, OpenAI when we train a very big, powerful model, they never release the model, but many people release the model, make it public, right? Then the question, if we think the model is a property, how do we leverage these existing models, right? So available on Hugging Face. All right, so there are different ways to leverage existing models. So first is just use the model as it is, right? You can use the model to maybe for transfer learning, maybe on the task that's similar the model was trained on, right? So the pros is that there's no training, right? You just use the model, there's no training. But the cons is that the model may not be good enough for your data set, for your task, right? Then the second approach is the fine tuning. This is actually what most people are doing right now for large language models because you cannot pre-train a model. A large language models, it takes a lot of resources. We just take a pre-trained model, maybe a fine-tuned model to do further fine-tuning. Right? So use the existing model as a starting point. So pros is that usually involves minimum training. You don't need a lot of GPU resources. But the cons is that your approach, your model will be restricted to the same structure. And usually fine tuning, there is a minimal, sometimes no improvement. Okay, depending on what data you have. Then there is a third approach called knowledge distillation. So knowledge distillation uses the existing model as a teacher model to train a smaller model, student model. So the process is that usually it improves the standard training, okay? But the cons is that it usually trains a weaker model than the teacher model. You cannot get a stronger model than the teacher model. So that's the limitation of knowledge distillation. Okay, so today I want to introduce you a new way of leveraging existing model. It's called model steering. Okay, it's what I call model steering. So model steering refers to a learning paradigm that leverage an existing model as a reference to improve the training on custom data sets through strategic data weighting or selection, and with the goal of improving the scaling law. Okay, improve the scaling, improve the generalization, improve the scaling law. So model steering, to achieve model steering, so we leverage reference model. So basically we use a reference model in our training algorithms. Okay, so the reference model could is an open model. Is maybe you model your trained on smaller data sets, maybe open model that you don't know what data set they use, what algorithm use. But you want to train a you want to train a stronger model on your own data sets, right? So that's what we want to do. That is model steering does. All right, so difference from the knowledge distillation is that knowledge distillation, as I said, usually requires a stronger teacher model to train a smaller student model, right? So this is strong to weak, paradigm, right? And it conduct regular training on the distilled data from the teacher model. Model steering is different. So we can train a stronger model by using a weak reference model. So we use a reference model in the training. We change the training paradigm. We change the training algorithms, right, to leverage reference model. So that's a difference. So that we can enable the weak to strong generalization. All right, so what is the regular training, right? So if you're familiar with machine learning framework, algorithms, they're mostly based on this framework called empirical risk minimization. So you have a bunch of data. So each data define a loss, right? Define a loss and average over these individual losses. And then you optimize this objective, right, by some stochastic algorithms, SGD, ADAM, momentum, ADAM, W, whatever. However, this framework is not enough, right, for leveraging the reference model. It's not enough for many other problems that we'll talk about later. Okay. Any questions so far? Okay, so let me move on to the framework or theory. It's DRO risk minimization. So the DRO risk minimization is actually built on a loss called row loss that leverage the reference model. So row loss actually not proposed by us, it's proposed by early works, studied in early works. So the idea is that because we have a reference model, right? So I know we have a model, target model we want to train, W here. So we can measure the loss of the target model on the data xi, and we can also measure the loss of the reference model on the same data, and we compute the difference. That is called row loss. So early works has used this row loss to select the data in the mini batch. For example, if you sample mini batch, and you can compute the row loss and you order that, and you only select the data with the top row loss. Okay, and compute the gradient of those top those data with the top row loss in your mini batch. Okay, and early works has found this is very effective for different tasks, for example, classification, large language models, etc. However, the most existing studies are kind of heuristic, ad hoc. I mean, there is a limited understanding why this works, how this can improve generalization, can improve the scaling law. And that is what we want to address. So we want to develop a principled framework so that we can understand the benefits. We can understand the generalization error, the scaling law, how it affects the scaling law. And also we want to develop the best practice, than the early works based on heuristics. Okay, that's what we want to address. So our framework is called the DRO risk minimization. It's actually leveraging a very powerful optimization tool called the distributionally robust optimization. So if you have this row loss, if you simply combine this row loss in the ERN framework, you do the average, empirical average over individual data, it does not help, right? Because the WR, this reference model, is a constant. This part is a constant, does not depend on W. And if you do the empirical average, that's the same as a regular training. Okay, so ERM is not enough, so we use this distributionally robust optimization framework. So the idea is that we assign each data with a weight pi. So the summation of pi equal to 1 and all the pi larger equal than 0. And then we take max of a p from the simplex, right? From simplex. And of course, we add a regularization here. So we add a regularization here. So the regularization is measure the KL divergence between the p, the weight p, and the uniform weights. And tau is a regularization parameter. Okay, so if we don't have those reference model, so that's the standard DRO, distribution robust optimization. But if we have the reference model, we have this part, we have the row loss here, right? So we have this DRO risk. So this objective here is a DRO risk. Okay, so and then we can minimize over W. But of course, this min-max problem is difficult to solve, and we can solve P first. Given W, we can solve P exactly, and we plug in back, and we give the closed form solution, a closed form expression in terms of W. Okay, we have tau is the regularization parameter. We have log. Inside the log, we have the average of all data, and then exponential the row loss divided by tau. And then you just minimize over W. Okay, this is the DRO risk minimization. Okay, this is the framework. So next, we want to understand how this framework can give us better generalization, give us better scaling law. Right? So we want to analyze from theory. Okay, so we develop theories based on the existing result of DRO distribution risk minimization. Okay, so we have two results here. So we want to bound the generalization error of the learning model by solving this object, by optimizing this objective. Okay, so this is a generalization error, which is measure the error of the model on all possible data, taking expectation of the underlying distribution. So we bound the generalization error. So upper bound here is big O. We have square root. Okay, we have square root. We have the variance of the row loss. Row loss calculated using the optimal model W star. So the W star is the optimal model that optimizes the underlying testing performance, testing error. Okay, so the variance, because the data is a random variable, consider data as random variable. So this row loss is random variable. We compute the variance. So the benefit here is that if we think the reference model is sufficiently trained, okay, sufficiently trained, you take an existing sufficiently trained model, for example, Meta Llama model or DeepSeek model, sufficiently trained, right? That model could be very close to the optimal model. So that this difference, this row loss, could have a very small variance, right? If we compare this generalization error bounds with the standard generalization error bound of empirical risk minimization, so that is big O square root 1 over m, a constant divided by m, right? So the difference is that the constant is reduced to the variance of the row loss of the optimal model, and the variance of the row loss could be very small, right? If the reference model is sufficiently trained. So that's the benefits of using this DRO risk minimization, using this reference model, right? So we can quantify the benefit. And then there is another result we developed. We want to compare the generalization performance of the learning model of our method with the reference model. Okay, we want to see how many data we need in order to achieve the same level of generalization as the reference model. Right? So this generalization error bounds, we have generalization error of the learning model bounded by that of the reference model plus big O 1 over m. Okay, big O 1 over m. N is the number of data used for training, right? So if the reference model is trained with regular training, so generalization error is, roughly scales 1 over square root of m. So m is the data size for training reference model. Think about, okay, if this model is a Meta Llama model, think about how many data they use. That's the M here. And if you want to achieve the same level, same order of generalization error, 1 over square root of M, and how many data do we need? M, that is roughly square root of M. Okay? So it's much smaller data size used for training the reference model in order to get the same level generalization performance.
So
Right?
can I ask one question?
Yes.
So so what I mean, do you assume that the data set used to train the reference model and the data set used to train the the target model follow the same distribution?
Yes. So here we assume they follow the same distribution.
Okay, yeah, thank
Yeah,
you.
because otherwise we cannot compare the generalization error, right? So we
Yeah.
assume that this generalization error is taking the underlying distribution of the data. We assume the same distribution. Yeah. Okay, so this result shows that this DRO risk minimization can reduce sample complexity dramatically. Okay, so there's a two theoretical results we developed, and then let's look at how we
Oh, by
apply
the
this.
way, another question. So then the target model, I assume that has much smaller size than the reference model.
So in these results, we assume the same size,
Okay,
but they can be different size,
okay,
right? So yeah, yes, it can be different size.
okay, thank you.
Yeah. Okay, so let's apply this framework theory to practice. Okay, so we want to consider a task for the clip training. Clip is short for contrastive language image pre-training. It's a type of self-supervised learning. It leverage the image text pairs, image, and the corresponding text captions. So we could get a lot of data from the internet. So OpenAI trained the first clip model, okay, on 400 million image text pairs. Right, so this clip model was trained in a contrastive way. So in the clip model, we have two encoders, image encoder and text encoder. So the two encoders trained in a way that for the image, we get an embedding. For corresponding text, we get an embedding. And we want the two embeddings as close as possible. I want the embedding of this so-called positive pair to be as close as possible. And embeddings for the negative pairs, image and non-corresponding text, we want their embedding to be far away from each other. Right? So this is the contrastive. Okay. All right, so let's talk about objective. Right, so let's think about image text pair. This is image corresponding text. This is the image kitty, and the text is kitty in the basket. So this pair is a positive pair. Okay, positive pair. So we want the embedding. So capital I is embedding of the image, capital T is embedding of text. We want their similarity. So this is the normalized embedding. This is cosine similarity. Okay, we want their similarity to be as large as possible. So we take a negative, so otherwise this is a loss. Okay, and this similarity is so-called negative pair similarity. So this image and another text not corresponding to this image, that's possibly a negative pair. So we want this similarity to be as small as possible, right? So we take this negative pair similarity minus positive pair similarity. That defines a pairwise loss. Okay, Lij. Okay, there's a loss. There's loss. And then we need aggregates over the J over the I, right? So let's first think about how to aggregate over the J, because there are many texts. J could be from 1 to capital N. So let's say there are N capital N text here in my data sets. Then the simple way, I mean, if you think about empirical risk minimization, you just do the simple average, right? You do simple average. However, simple average, this is a very bad idea, because that N is usually very large. N is usually very large, and among this N tags, many of them are easy tags, so you can easily make their similarity to be very small. And only few of them are hard negatives. They're kind of similar to the true text, but not the correct text. So that's hard negatives. But if you do the empirical average, and if you do random sampling, you can imagine that you can rarely sample the hard negatives. That is what we want to learn from hard negatives. But the simple average cannot do that. So this is a very bad idea. So in practice, we don't do that. So in practice, we use the so-called contrastive loss, or some people call it info NCE loss. But our objective is a little different. Okay, I want to talk about difference. So this global contrastive loss for ice data is the tau, the temperature parameter. People call it temperature parameter. Log, inside the log, we have average of all text and exponential of the pairwise loss divided by tau. Okay.
So I have one question about constructive loss. So if n is very large, then the total number of pairs is very large. And for
Exactly.
large language models, this may lead to large memory and computational cost. So
This is just a formulation. This is the formulation, but in practice, later we'll show you the algorithm for solving this. We don't need very large, batch size and memory cost.
Okay, thank you.
Okay, so but this formulation is very different from existing study from industry companies, from OpenAI's approach. Existing approach is just use a mini batch here. You just use the mini batch inside the log, because of course you can think about, okay, this is the reason for the computation purpose, but the problem is that if you use a mini batch, you need very large batch size to get a good performance. So later I will show you the batch size OpenAI use very large batch size, which means you need a lot of GPUs, but we don't need that. Okay, but our formulation, again, we want to solve this objective here, that sum of all data. And we show you algorithms for solving this very efficiently without using large batch size. All right, so this is the global contrastive loss for ice data, and then you average over the n data, n images, you get global contrastive objective. And of course, for contrastive, for the clip training, you have another term. You do the similarly, which is you contrast each text with all the other images. We just combine them together, but it's similar to this term, so we just ignore that. Okay, so but this framework we cannot leverage reference model, right? So this LIJ is based on the target model, right? So you have a target model, you have the embedding, you compute similarity, and then you get the pairwise loss, right? So how can we leverage the reference model, right, to improve the training? So again, so this is based on our early work, the connection between global contrast loss and the DRO, distributionally robust optimization, right? So actually, this equivalence has been shown before, right? This is tau log average exponential. This is equivalent to DRO, distribution robust optimization. So here we assign weight to each J, PJ, right? So the PJ from the simplex and the KO divergence, tau is regularization parameter, and max over P. So these are equivalent. Okay, this is equivalent. So this means that we can apply DRO, right? Risk minimization to this framework. We just change this loss to the row loss, right? Very simple. We just change this pairwise loss to the row loss. Okay, so that is our final formulation. So that's apply DRO risk to the clip. Okay, just change this pairwise loss to this row loss. So use the reference model to calculate the pairwise loss, and you have target model to calculate pairwise loss, and then you have the difference. You put it over there. And that is your objective, and you want to minimize over W. Okay, so that's the DRO clip formulation, and it will solve it efficiently, and we train the model, and that is the DRO clip. Okay, so next, let me show you some results. All right, let me show you some results. So this is the results we compare with OpenAI's clip model. So we use OpenAI's clip model as a reference model. So OpenAI, they train the model with 400 million data image text files. They release the model, but they don't release the data. They train the model with more than 30K batch size. This is roughly more than, they need a couple hundred GPU to do that. One GPU, it can only hold maybe, few hundred batch size, but for this large number of batch size, you need many GPUs. And they train the model with 12.8 billion samples. Okay, this is the compute budget. sample C. So we use this OpenAI clip model as a reference model in our framework, and we train a new model called DRO clip. Same model structure, okay? I think so. So we use 2 times less data size, 192 million image text files, and we only use 5,000 batch size. And this is roughly, we can hold this for 8 GPUs. Okay.
One question here. So 192 million data. So is this a subset of the 400 million data, or is a different data set?
It's actually different data because I said they don't release the data sets because
Okay.
later on there's OpenAI, there's a community collects like Lion, like Data.com, they collect some data set from the internet.
Okay, thank you.
But all the data is coming from the internet. Okay. So we only use 10 times less compute budget. So basically we use 1.28 billion sample C. Okay, 10 times less compute budget, 6 times less batch size, 2 times less data size, and we use the OpenAI clip models reference. We have 5% improvements on the ImageNet 1K classification. This is 1,000 class classification task. So 1% improvement is significant improvement. Okay, so this means that now if you have 8 GPUs, you can train a model better than OpenAI's model, right? You can even train a model, probably get a state-of-art performance. You don't need to worry about you don't have a lot of GPU resources, right? Okay, and also we did a lot of ablation studies. So here we compare to the regular training. So the fast clip is actually what we proposed before. This is a regular training of clip model. We compare the DRO clip with different size of training data. So I mean, with a different reference model, so it's either open weight model released by other people, or we train our reference model on the smaller data sets, and then we can reduce the sample complexity. In the first 2 cases, we use 50% of data, we get the same performance as the regular training with using all the data, 100% of data, right, on the CC12. And with 70% of data, we can get a better performance, much better performance than the blue line, than the baseline. Okay, so that's reduced sample complexity, right? So that's validate our theory. And also we compare with other baselines, open clip, fast clip, and so this is a regular training. So improvement of fast clip is that we don't need very large batch size. And also Google's approach, JAST, that also use the real loss reference model. So JAST is a heuristic approach, right? It's just a heuristic approach. And you can see that DRO clip has dramatic improvement over the heuristic approach. And another thing is that DRO clip can be easily combined with knowledge distillation. If you have a stronger model as a reference model, for example here, very strong model as a reference model, you can incorporate the distillation loss into the objective. You can get a better performance. Okay, so can easily combine with knowledge distillation. But if your reference model is not a strong model, for example here, right? It's not a strong model. You train a model stronger than reference model. That in this case, knowledge distillation does not help. Okay, but model steering still help. Okay. So this is ImageNet top 1 accuracy. This is the Data.com that evaluates on a bunch of maybe more than 30 kind of classification retrieval tasks. We all have consistent improvements. So finally, I want to show you the scaling law, improved scaling law. So this shows the scaling law of the ImageNet error versus compute budget. So we experiment with a different model size, VITB 32, VITB 16, VITB large, different model size. Okay, so for each model size, we vary the data size, we get the best performance, and plot the point here. And then we plot this curve. This is a power law. This is a scaling law we're talking about. And you can see that the orange curve is our algorithm, has a better power constant here. So that means we have better scaling law. Okay, so we can use less compute budget to deliver a much better performance. So that is, you know, the benefits, what we have, right? All right, so that is the methods applying the framework to the clip training, but you can actually apply the framework to many other problems, you know, classification problems, even large language model training, right? You can apply that. Okay, so next let's talk about optimization algorithms. Are there any questions? Okay, so let's move on. Optimization algorithms. I want to talk about very useful optimization framework and algorithms, and could be very useful in many tasks. And we use this same optimization techniques for solving the objective I talked about earlier. So this framework is called empirical X risk minimization, EXM. This is based on the research that we conducted in the past 5 years. We have done a lot of research on this problem. So this is the framework, okay? So we want to go beyond empirical risk minimization. Remember we talked about empirical risk minimization? So each data define the loss and the average. There is a basic assumption in ERM. The assumption is that we assume the loss for each data. We can easily compute the loss and its gradient. That's a basic assumption. You assume the loss gradient of each data loss can be easily computed. But that is not true for many problems. For many problems, that's not true, okay? For example, the glib training. So in order to capture the complexity, we formulate this mathematical framework here. So for each data, my loss has a structure. It's a compositional structure. It's a composition of two functions, f of g. F is usually a simple function, but nonlinear and possibly non-convex. The inner function g not only depend on this data xi, but also depend on a large set si. This si contains many data points. So a simple form of the g is the average of all the data in the set si, and you combine, you couple xi and xj from the set, you define the pairwise loss. So this is very general framework, actually captures many problems, okay? And I will talk about that. So global contrastive loss, the global contrastive objective that I talked before is actually a special case of the empirical X risk minimization. So here it's mapped the log to the f function. Log is f is nonlinear, non-convex. And inside the log, the average over j, right? So that's the inner function g. The inner function d depend on i's data, but also depend on many other data j, right, from 1 to n. And so that's si contains all other text, xi is the i's image, si is all other text. So the global contrastive objective is X risk. Okay, how do we solve this? Right. So the challenge is that how do we compute a gradient for this objective using mini batch, right? We don't want to go through all the data. We cannot do that. Right. So the challenge here is actually there are two summations. Summation here, the outer summation and the inner summation. Both sum over many data points. So previously in ERM, we don't worry about the inner summation. We assume this individual loss gradient can be easily computed. And then we approximate the outer summation by the mini batch, right? Just compute the mini batch. But here we have the inner summation we need to deal with. Okay, so let's look at the optimization challenge. Different from ERM. ERM, as I said, assume each loss, individual loss gradient can be easily computed. And then you just approximate the average by the mini batch average. You get the mini batch loss, mini batch gradients. That gives you unbiased estimate of the true gradient, right? The expectation of the random sample give you the true gradient. That's the ERM framework. But in the empirical X risk minimization framework, for each individual data xi, we cannot compute the gradient, right? So the gradient is gradient of f at inner function value of g times gradient of g. But both the value of g and the gradient of g depend on large set si, right? Okay, so you might think, okay, why don't we just use a mini batch to calculate the value of G and the gradient of G? Okay, so that's the formulation here. We just use a mini batch, right? And this is exactly what industry companies existing work do. They just do the mini batch. You just sample mini batch and compute a mini batch loss, mini batch contrastive loss, info NCE loss, and then do the back propagation that gives you exactly the same this mini batch gradient. But the problem is that because f is nonlinear, if you take expectation of the mini batch, does not give you the true gradient. Okay, this is a biased gradient. That's the difference because the f is nonlinear. So if you have a biased gradient, then all the existing algorithm theory will fail. And if you want to analyze the generalization error, optimization error, that will depend on batch size. So estimation error of this gradient estimator will depend on batch size. The smaller the batch size, the larger the error. So that's why in practice, they need very large batch size. You see, OpenAI use more than 32,000 batch size. But in the traditional deep learning, when we think about ERM, we don't need that large batch size, right? Use only 256, good enough for example, ImageNet classification. But for contrastive learning, you cannot do that. If you use this mini batch approach, you have to use very large batch size. So that's why, this kind of clip training is only doable by big companies like Meta, like OpenAI, like Google, because they have a lot of GPU resources. That's the approach they are doing. Okay, and we want to address that. We want to use small batch size, regular batch size. We can still deliver the same performance as very large batch size. We want to address this challenge, and this can be addressed by, advanced optimization algorithms. So this is the core idea of our algorithm. It's very simple, very simple. Okay, so key idea is that, as I said before, if you simply use the mini batch estimator of the G value inside F gradient of F, that'll give you a large estimation error. So the idea of our algorithm, the SOX algorithm, actually in our earlier paper, we studied the theory. We just maintain and compute a different estimator of the inner function value G, okay, denoted by UI, okay. As a key iteration, we update UI from UIT to UIT plus 1. Simple average update, right? So we still compute the mini batch estimator of the G, but we do not simply use that G inside F. We combine this mini batch estimator with the previous estimator UIT with moving average. Gamma T is a value between 0 and 1. This is just moving average estimator. And the only contact for data in the mini batch. If the data is not sampled, not in the mini batch, just keep the original value. Okay, so you can see that computation is almost same as the regular, the previous approaches based on the mini batch, right? We'll only use the mini batch, calculate mini batch gradient of G, mini batch value of G. We just do this simple update. This is a scalar, right? Simple update. Okay, this is the minimum overhead. Okay, and then use UIT plus 1 inside F compute gradient estimator. That's it. And then you can use whatever optimizer you want to use. Adam, momentum, Adam W, whatever you use. Just this is the gradient estimator. Okay, and we can prove that this algorithm can converge without using large batch size. We can make the optimization error goes to 0 with small batch size, regular batch size. Okay, that's the benefit. Okay, so let me show you some results we got earlier. So apply that algorithm, SOX algorithm, to unimodal controlled self-supervised learning that give us SOCLEO. So compare SOCLEO with Google solution SimCLEO that is based on mini batch approach, mini batch info NCE loss. The Google's approach, SimCLEO, needs very large batch size. So this figure shows the performance on ImageNet versus batch size. So Google SimCLEO needs larger batch size, more than 4,000, 8,000 in order to get a good performance. But we only need, let's say, 256 to get the same performance as Google solution using more than 8,000, 4,000 batch size. Okay, right. So now you don't need very large batch size to do this contrastive learning. And also we can extend the framework to optimize temperature. You see, remember there is temperature parameter tau. In the DRO framework, we can also optimize the temperature. So this gives the better performance than the standard CLIP training method. Okay, so the standard CLIP training just use a heuristic approach to optimize tau, but we can optimize the tau in a better way. And fast CLIP again is basically is a distributed training framework based on these optimization algorithms for CLIP training, right? So compared to open CLIP, we don't need large batch size. Open CLIP again is based on the mini batch contrast loss, info NC loss. They also need very large batch size to get the same good performance. If we use the same smaller batch size for open CLIP, we have much better performance, faster convergence, better generalization. Okay, and also, as I said, the X risk covers not only the global contrast loss, but many other losses. You can think about areas and the curves that includes area and ROC curve, area and precision recall curves, partial area and the curves, one-way partial area and the curves, two-way partial area and the curves, ranking measures that includes NDCG, list-wise loss, list net, list MLE, p-norm push, top K of this performance. They all can be written in the same framework. This framework, the compositional framework, optimization framework, and our algorithm can be used to optimize all of these measures objectives. Okay, so that's why we implement this algorithm in our library. We developed a library called the libaoc. So originally, this libaoc just to have this algorithm for optimize AORC that we did 5 years ago. But later we have this general framework. We can optimize a bunch of measures, in this framework. So currently, this libaoc library is intensively used by the communities. Has been used by people from more than 85 countries, and up to this point, we have more than 88K downloads. Every month, there are more than 1,000 downloads. People use this in their research, in their project. So so if you have imbalanced data, you want to optimize this ranking measures such as AUC, partial AUC, average precision, and if you also consider ranking problems, recommendation problems, you want to optimize these ranking measures, ranking objectives, and also of course self-supervised learning. You can consider using our library. And also our library has been used to solve real-world problems. For example, we won the first place at the Stanford Checksburg competition. This is for classifying X-ray images, right? So the measure is AUC. We directly optimize AUC. We get the best performance. And also this library, libaoc library, helps us win the MIT AIQs challenge. And so this challenge is for classifying the properties of molecules such that we can find molecules to design a drug to fight COVID during the pandemic. So my colleague, Dr. Sri Wang's group, used our library to get the first place. So without using this library, libaoc library, so their original performance actually is the third place in terms of AUPRC. But using our library, we improved that to the first place. So there is a 5% improvement in terms of AUPRC. And also there is a 3% improvement in terms of AURC. So there's a dramatic improvement because this data is highly imbalanced, only like 0.2% positive data. So it's a very, very challenging data set. Okay, so that's all I want to share. So finally, I want to use this quote from Donald Knuth to conclude this talk. So the best theory is inspired by practice. Actually, this empirical X risk minimization framework, the theory framework, the theoretic framework, is inspired by this challenge. When my colleague, Dr. Shui Wangju, asked me that, how do we optimize AUPRC? So I formulated the first objective and later on found that that framework is very very generic, covers many objectives. So that is coming from, inspired by practice. And then the best practice is inspired by theory. So this DRO risk minimization framework, you can see that the theory is very useful to deliver the best practice. Okay, so that's all. Thank you, and I'm happy to take any questions.
Yeah, thanks, Professor Yang, for your very insightful talk. Now we have 10 minutes to answer questions. If you have questions, you can post your questions on the chat box, or you can directly ask. Yeah, I think please look at there's one question posted on the chat box.
Okay, so question, given that human creativity often comes from cross-domain learning, is it practical to steal model using multiple specialized reference model? I think this is a very good question. I think yes, it's possible. Also, when my student present this paper in our group seminar, also students also ask this question: how do we use multiple reference model, right? So I think definitely, some reference model may be better than other reference model on some data sets, right? So then you have to think about, okay, on this data set, maybe I use this reference model, or maybe use a combination of these different reference model. On other data sets, I may use another reference model or another combination of the reference model, right? So I think it's possible.
Thank you. So any
Uh,
other questions?
if there is another question, is there existing framework allows the model to leverage this together? I don't think so. I think so I mean this framework, the model steering or the learning with reference model is a pretty new area. Not a lot of studies. So I showed several studies that only a few studies available right now, I think. But this is a very promising area. Um, I think more people can work on this problem. From theoretical viewpoint, yeah, I think definitely. I mean, we probably need to develop some other theories for accounting that. Okay. So another question: how generalizable DRO beyond the vision language model, like uh, beyond vision language model? I think it's very generalizable. As I said, in the early works, people have already explored this for classification tasks for large language model training. Uh, um, I think it's very generalizable. So you can think about using this in different problem, different models.
Yeah, maybe yeah, one question. So for constructive loss, as you mentioned, typically we need a large batch size. Otherwise, the test performance is not good. And so I mean, I guess there are other different approaches that can use small mini batch size that can achieve um, good performance for constructive learning. So did you compare your algorithm with existing algorithms that were designed to make the batch size small?
Yeah, I do. Actually, in our first paper, SML 2022, at that time, there are some other works, trying to also address this issue with some other approaches. For example, they kind of also change the mini batch loss. So for example, debounce the contrastive loss. We do compare with that in our first work. I think this is better. This is better. But later on, uh, we just, I mean, in the clip training, because open clip is the standard state of art, we just compare with clip, open clip in the later clip training works. But in the first work, contrastive learning, we did compare with other approaches.
Yeah, thank you. So
Yeah.
there's another question posted.
Okay, let me see that. Okay, I think this is a very good question. So let me give you insights. Okay, yeah. So the insight is that if you think about, the baseline approach, right? the baseline approach uses mini batch, but large mini batch, right? So we need a large mini batch. But if I only have small batch here, how can we increase the mini batch? We can leverage the data we use in the previous iteration, right? So if the model, let's say if the model converge, if the model WT and WT minus one very close, so basically the mini batch data we use in the last time can be very useful for this time, right? Although it's computed on a different model, WT minus one, but if WT minus one, WT close, because eventually the algorithm will converge, WT minus one will become closer and closer. So the previous iteration, the previous estimator will be very useful to estimate the G at the current iteration, right? So that's the insight. Okay, so with the model, when the algorithm converge, when W becomes closer and closer, the previous iterations, the mini batch we use in the previous iterations that we calculate the estimate of G could be very useful for the current iteration. So that's why we incorporate the history, right? UID is a history. We incorporate the history into the current calculation. And also from theoretical viewpoint, we can show that the error between this U estimator and the G estimator and the G function. Okay, so the difference between UIT minus one minus the exact value of G at WT, this error will goes to zero. Okay, this goes to zero. So if you average the zero of all iterations, so that average goes to zero. But if you use mini batch, that error never goes to zero. Okay, so that's the intuition.
Yeah, thank you. Constructive learning is now very popular. So there may be different versions of constructive loss defined for different problem settings. So is your algorithm applicable to all versions of constructive loss, or are there specific conditions that must satisfy in order to use your algorithm about constructive loss?
I'm not sure what contrastive loss you're talking about. So here, I mean the clip contrastive loss and Google's SimClear for image data, they kind of share the same structure, so-called. I mean, in the literature, people think about this is info NCE loss. So they eventually take the same form, which is log. Inside the log, we have sum over a bunch of data, right? So that's the form. As long as you have this form, this algorithm can be applicable. And also, if your problem have this particular form, so of simple function f and a composition with another function g, then this algorithm can be also applicable.
Yeah, so here L, right? So the L function in the G function. So L here can be any nonlinear function.
Can be any nonlinear function. Yeah.
Differentiable, right?
Differentiable. Yeah. Any nonlinear function.
Oh yeah.
Yeah.
Great. Thank you. I think we all have only 2 minutes left. Any other questions? Why inner interpolation works? I think this has already been answered.
I hope that has been answered.
Yeah.
I mean, yeah, I mean, there could be other ways, but we can right now we can prove this simple way will work, right?
Yeah.
And you can also think about this is actually doing stochastic gradient descent on another problem. So basically, you can construct a problem like this. So let me show you. So you can construct a problem U minus the G square. So this is the problem and the W here. And if it's the stochastic gradient descent of this problem, and you get this update, right? And so it means that you can change this to some other updates for optimizing this quadratic problem, right? This is not only way, you can have some other ways. Yeah, but this is very simple, yeah.
Yeah, thank you. I think it's already um 12 p.m. And I would like to thank Professor Yang again for your very insightful talk. Actually, we have one ongoing project. We have the same issue that it's a constructive learning, and we cannot decrease the batch size, otherwise the performance is very bad. So I'm definitely we will use your your algorithm, and we'll keep you posted if we observe good performance.
Yeah, actually, this our algorithm has been used by many other people also in their paper
Yeah,
work. And it works. Yeah, I
yeah,
mean,
we'll
if you
keep
have
you posted. Yeah,
anything you want to discuss, I'm happy to discuss.
yeah,
Yeah.
yeah. It's a constructive learning for language models. Yeah.
Okay. Great.
Thank you so much again, and have a good weekend. Bye.
Good. Thanks everyone.
Bye
Bye.
bye. Thank you, everyone.